Hi everyone, welcome back. In today's lesson we're going to be talking about differentiation formulas. And these differentiation formulas are going to help us streamline the whole derivative taking process. So we're going to be able to take derivatives faster without having to rely on that limit definition that could potentially make them take longer. And what I have here on the screen are these differentiation rules. It starts off by saying, let C be a constant and f of x and g of x are both differentiable functions and n is a real number. Well, the first one that we get is that the derivative of a constant is equal to 0. Okay, well that kind of makes sense because if you have a constant function, meaning a horizontal line as a graph for that constant function, then when you're looking at its rate of change, there is no rate of change, which means the rate of change is going to be 0. So again, this is the derivative of a constant. Number 2, this says that the derivative with respect to x for some x to the power of n, and again this is going to be some power function, then what we do is we take that we take that exponent n, we drop it forward, and then we subtract 1 from the exponent. The result will be our derivative. We also have the derivative of a constant multiplying by a function with respect to x. This says that when we can take the derivative of a constant multiplying a function, we can technically bypass that constant because the derivative will have no effect on that constant if it's multiplying your function variables. In that particular instance, you'll be left with the constant c multiplied by the derivative of the function evaluated at x. And this is known as your constant multiple rule. Number 4, this is that we can take the derivative with respect to x of two functions that are either being added or they're being subtracted. So again, it doesn't matter whether we are adding or subtracting these two functions in which we'll be taking derivatives, but when we do, we could then take the derivative of the first function, that's f prime of x, add it or subtract it, whichever sign we were initially looking at or working with, and then add that or subtract it to the derivative of the second function, which would be g prime of x. Number 5 and number 6, these are one of the more crucial, important differentiation formulas that we will need. And these formulas are formulas that they will have to be ingrained in you as you proceed through the rest of your calculus coursework. Not only in this class, but in Calc 2, in Calc 3, in differential equations, in linear algebra, and anything above that, you will need these differentiation rules to be in your mind at all times. Number 5 says that when we take the derivative with respect to x of two functions, f of x times g of x, we get the first function, f of x, multiplied by the derivative of the second function, plus the derivative of the first function multiplied by the second function. And this is your product rule for derivatives. So again, you might hear at a later time, oh, you need to use a product rule when you're taking that derivative. It means that you need to apply this rule. Secondly, number 6, we're going to have the derivative with respect to x for the quotient function f of x divided by g of x. In this particular instance, for the quotient rule, it says that for your numerator, you will have the derivative of the first function multiplied by the second function g of x minus the top function f of x multiplied by the derivative of the bottom function g prime of x, all divided by the bottom function squared. In other words, g of x squared. And so again, these two formulas you must know, you must have them memorized as we start progressing through the semester. Now, one of the items that I want to look at first is going to be that we want to prove the product rule for derivatives. Now, again, the product rule says that, well, if we have the derivative of a product of functions, f of x times g of x, then this must equal to f of x times g prime of x plus f prime of x multiplied by g of x. Okay, so this is what we're going to go with. And in order to start this proof, I'm going to say let f of x and g of x be differentiable functions, and we're going to say that f of x, capital F of x, is equal to lowercase f of x multiplied by g of x. Okay, so why did I want to start with these two functions being differentiable and then take a product of them? Well, if you notice for that differentiation rules at the very top of your screen, the differentiation rules would start let c be a constant, and then we have that f and g are both differentiable functions. So that has to be a given for this particular proof, because again, we're trying to take the derivative of two differentiable functions and we want to make sure that we get the right hand side, which again turns into that product rule. So looking at this, what I want to do at this particular instance is I want to go ahead and elaborate more on g of x and f of x. So I'm going to say, since f of x and g of x are differentiable, we get that f prime of x is going to be the limit as h is approaching 0 for f of x plus h minus f of x, all divided by 0. And we also get that g prime of x is equal to the limit as h is approaching 0 for g of x plus h minus g of x, all divided by h. And again, this is what we get because we stated that f of x and g of x are differentiable. So that's going to be awesome. So what I'm going to do now is I'm going to start looking at my derivative f prime of x. Okay, well, if f prime of x, since we're going to have two functions that are multiplying each other, f of x and g of x, and they're both going to be differentiable, it's going to stand that I'm going to be looking at a differentiable function, f prime of x, and that's for my capital F. Now, in this particular instance, I then want to then extract what it's going to look like. And in this case here, f prime of x, for a capital F prime, this is going to look as a limit as h is approaching 0 for capital F of x plus h minus f of x, all divided by h. And so again, I'm just using that limit definition for the derivative. But capital F of x has a different representation. That representation is lowercase f of x multiplied by g of x. So in that case, what I'm going to do here is I'm going to start making my substitutions. Capital F of x, when I insert x plus h, is going to look like f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Awesome. So now let's keep going with this. And we're going to get crafty here, because getting crafty at this point in time is going to help us factor this numerator. And so what I want to do is I'm going to insert negative f of x times g of x plus h, and then plus f of x times g of x plus h. And then I have my minus f of x times g of x. That's one big fraction. Wow. Pretty cool. Okay, great. All of this is still being divided by h. Now again, what I did from the previous line was I just inserted, look at what I inserted. I inserted negative f of x times g of x plus h plus f of x times g of x plus h. And what happens here is that these two terms will essentially cancel each other and leave us with the previous step. However, we don't want to go backwards, so that means that we don't want to cancel these out. Well, instead, what we're going to do is we're going to group them. And so when we group these factors, what I'm going to have is in the first two terms, and I'm going to highlight my first two terms. In these first two terms, what I'm going to do is I'm going to factor out what they have in common. And what they have in common is g of x plus h. So for that first term, g of x plus h is going to multiply f of x plus h minus f of x. For the second term, plus, I'm going to see what they have in common there. And again, let me highlight this to say that was my first piece. The second piece is f of x plus g of x plus h minus f of x times g of x. And again, I'm going to factor out what they have in common. So what they have in common is an f of x, and I'm going to multiply now by what remains, f of x plus, g of x plus h minus g of x. And this is all being divided by h. Perfect. Awesome. Okay, so now what I'm going to do is, now taking the limit here would be quite nice, so I'm going to actually do it this step by step. Okay, I'm not going to take the limit just yet. Instead, what I'm going to do is this. I'm going to separate my factors as such. And that factor is going to be divided by h. There we are. So now you can see that because we've separated now our fraction, we've separated our fraction into two different terms that are still being divided by h, which means everything is still the exact same. The only difference now is that I now have my h divided by its, let's say, its preferred divisor, or its preferred numerator, simply because I now have f of x plus h minus f of x divided by h, and again, g of x plus h minus g of x all divided by h. So now if I can take the limit here of these two terms individually, and which we can by using our limit laws, this is going to say that as the limit for h approaches 0 for g of x plus h multiplied by this particular limit, which will be the limit as h is approaching 0 for f of x plus h minus f of x, all divided by h plus the limit as h is approaching 0 for f of x multiplied by the limit as h is approaching 0 for g of x plus h minus g of x, all divided by h. So now all we have to do is keep taking these limits. Well, what's going to happen for the limit as h is approaching 0 for g of x plus h? Well, since this h is going to be approaching 0, that means that this function g of x plus h will only be left with g of x. Well, what about the one that it's multiplying? Limit as h is approaching 0 for the difference quotient. Well, remember that difference quotient was actually up here at the very top. So what is that? That's your f prime of x plus the limit as h is approaching 0 for my first function f of x. Notice, since this f of x doesn't have a factor of h or a constant of h, then what's going to happen here is that this is not going to be affected by this limit at all, and therefore the result for the first factor in that second term, the limit as h is approaching 0 for f of x, remains as f of x. However, that second limit now that we're looking at, or the second factor that we're looking at here, that's going to be the limit as h is approaching 0 for g of x plus h minus g of x, all divided by h. And in this case, that is the limit that we're looking at the very top of your screen. That is g prime of x. Therefore, we're left with f of x times g prime of x. And again, on the left-hand side, well, on the left-hand side, we had initially taken the derivative of this function f of x, right, because that was my f prime of x. But then that derivative for that f, capital F of x, is really just the derivative of f of x times g of x. Which means that we've actually proven that when we take the derivative of a product of functions, f of x times g of x, that we actually wind up with g of x times f prime of x plus f of x times g prime of x. So this is what we're looking at, and again, this is what we were proving, which means we're done with that proof. Awesome. Now, there are different proofs in your book for the sum and difference formulas for derivatives and the quotient rule. So my suggestion would be to look over those proofs and, again, familiarize yourself with those proofs. That way, if I ask something similar to that on an exam, then you're already well versed on how to take these proofs. Great. So let's go ahead and let's start elaborating just a little bit more as to what I'm going to be looking for and how I'm going to be looking at specific product rule derivatives and quotient rule derivatives. Okay, so one of the things that I will be using for the notation is going to be that when I look at my product rule, I typically don't like to look at it as f of x times g of x. I typically just like to look at it as, let's say this is d dx of some function of u times some function of v. then when I look at these derivatives, I just say, oh yeah, that's just u prime times v plus u times v prime. The quotient rule for the derivatives here, and you know what, we can get away with not doing ddx. We'll go with u divided by v prime. Then what's going to happen here is we take the derivative up top, multiply by the bottom, so it's u prime times v minus u times v prime, all divided by, and this is going to be all divided by v squared. And so oftentimes I have this in my head, and again, when I'm working with certain product rules, I'll make sure to whisper to myself, oh yeah, that's just u prime v plus u v prime, or something to that effect when we're working on those derivatives. All right, so now that we have this, let's go ahead and let's start working with some examples. So let's give a shot to some examples here. Now, these examples are going to be from the previous section when we were looking at the derivative as a function, and we were extracting what were those derivatives using the actual limit definition for derivatives. So for the first example, we're going to find f prime of x, where f of x is equal to 80x minus 6x squared. Now, we know the answer to this because it was in the previous lesson. So if you want to see the long way to do it, well then I'll leave the card on the right-hand corner of the screen and you'll be able to click on it through YouTube. But for now, we're going to make sure we use our differentiation rules to bypass the whole purpose of limits and just to take these derivatives directly. So as we're looking at applying the derivative here, ddx of my function f of x, this means that I'm going to have to take the derivative of the right-hand side, which is 80x minus 6x squared. And in order to do this, we're going to have to distribute the derivative across the first function, that's 80x, minus the derivative of 6x squared. Okay, so now we can go through and we can start using our derivative laws. Look at the first one, 80 multiplied by x. 80 multiplied by x turns into your constant multiple rule, in other words, rule number 3. And using that multiple constant rule here for this one, it's going to say just take the derivative of x. And when we take the derivative of x, we're going to drop the exponent forward. The exponent on this x is 1, so it's 80 times 1. So this is 80 times 1 multiplied by x, and then we subtract 1 from the exponent, so that's 1 minus 1. Minus, again, this constant multiple, this constant comes out, and then we're using the power rule. The power rule is rule number 2 for those differentiation rules. We drop the exponent forward, so this is 6 times 2, and then we multiply by the resulting function when we subtract by 1 on the exponent. Well, what do we get now? 80 times 1, that's just 80. X to the power of 1 minus 1, that's going to just be 1. Or at least x to the power of 0, which is 1. So for the first term, we get 80. For the second term, we get 12x. So there's our derivative. Now remember, this derivative, when we did it in the previous section, took us about 5 or 6 lines using limit rules. Now we're bypassing all of that and we're just doing this using our limit laws. Or sorry, using our differentiation laws. Okay, so that looks pretty good. What about this next example? Where we'll find let's go with g prime of t, where g of t is equal to 1 over the square root of t. Now, again, we did this on the previous lesson, and we did it using the limit definition for derivatives. Again, I want to bypass that. So in this instance, what I'm going to do is I'm going to take the derivative with respect to t for the function g of t. This means that I'm going to have to take the derivative for 1 over the square root of t. Now, I'm also going to note here that 1 over the square root of t is the exact same as t to the power of negative 1/2. Okay, both of these are equivalent, and I want to use the one that has an exponent for my function. It'll make things a whole lot easier. And the reason I say they're going to be a whole lot easier is because now when I take the derivative of t to the power of negative 1/2, I drop the exponent forward, so that's negative 1/2, and that's now going to multiply my function t to the power of negative 1/2 minus 1. And again, when we take the derivative, we always subtract 1. Well, let's keep working this out. Negative 1/2 minus 1, this gets us negative 3/2, which means t to the power of negative 3/2 for this function is going to leave us with negative 1 divided by 2 multiplied by t to the power of 3/2. And that's the same answer that we were left with last time, except last time, again, we took about 6 or 7 lines just to get this done. So again, we can streamline this whole process, and this is what we want to streamline as we keep moving through. We want to make sure that we can keep taking these derivatives quite fast. Let's keep going. Let's try some more derivatives. So we're going to say differentiate the following. Part A, we're going to be working with f of x is equal to 7/4 times x squared minus 3x plus 12. We'll do part B on the right hand side. Part B is going to be y is equal to x to the power of 5/3 minus x to the power of 2/3. Alright, so let's work with part A. And what you're going to notice is that I'm going to start moving faster and faster while taking these derivatives. Meaning I'm not going to be writing out step by step how we're taking these derivatives. Instead, it will be a subconscious effort to say the derivative is distributing into every individual term within that polynomial or within that expression, and then we can identify that we can take those derivatives term by term. And that's what's happening here for this f of x. When I take the derivative f prime of x for my function f of x, well, my first exponent is going to drop forward, so this is going to be 7/4 multiplied by 2 times x minus, minus, taking the derivative here of x, drop the exponent forward, subtract 1 from the exponent. That means that x turns into a 1, and then we're going to be left with negative 3. And the derivative of a constant, remember the derivative of a constant is 0. Therefore, when we take the derivative of 12, then we just get 0. And that's where this 0 is kind of coming into play here. And we typically just don't write the 0. So in order to get this f prime, 7/4 times 2, that's going to reduce to 7/2 x, and then we have minus 3. And there you are. That's your derivative. Looking pretty good. Let's go with part B. All right, going with part B, what's going to happen here when we take this derivative, so y prime, we're going to distribute that derivative, okay, for each individual term, and then you take the exponent for those x values and you drop them forward, so 5/3, and then you subtract 1 from the exponent. So that's going to be 5/3 minus 1 minus, do the same thing here, 2/3 times x to the power of 2/3 minus 1. So our y prime turns into 5/3 times x to the power of, and that's 3/3, so that's going to be 5 minus 3, so that's going to be 2/3 minus 2/3 times x to the power of negative 1/3. Check that out, that's awesome. Now, typically in math, we don't like to be left with negative exponents. So what I'm going to do is I'm going to factor out x to the power of negative 1/3. And that's exactly what I'm going to do here. Okay, so I'm going to write that I need to factor out the term with the negative exponent. Factor the, let's say, GCF of x to the power of negative 1/3. So that's a factor that I want to pull out because, again, it has a negative exponent. So factoring that out, I get x to the power of negative 1/3. Oops, here we go. And actually, there's a little bit more. The GCF 1/3, I believe. 1/3 x to the power of negative 1/3, as such. And the reason I wanted to pull out 1/3 is because both of the terms are being divided by 3. Therefore, I can pull out that factor that is dividing them by 3. Now, for my first factor, when I distribute x to the negative 1/3 back in, I should naturally get some value for x to the power of 2/3. So what number plus negative 1/3 gets us 2/3? So again, when we redistribute, what number for this exponent will add negative 1/3 plus that number to get you 2/3? Well, that exponent is just 1. And again, we still have a 5 from this numerator, minus 2/3. Well, we took out that 3, so it's just minus 2. And we took out the factor of x to the power of negative 1/3, so it's just this. Look at that. Nice. And again, we don't want negative exponents, so I'm going to make that negative exponent disappear. 5x minus 2, all divided by 3 times x to the power of 1/3. And there is your derivative. That's nice. So no negative exponents remain. And that's awesome. And again, that's what we want to see, is that no negative exponents remain at the very end. That way we can keep working with this particular derivative. Awesome. All right, good work so far. Now, let's work on a different example. So let's go with part C. For part C, what if I had y is equal to, let's say, 3t minus 1 multiplied by t plus 2? Well, what I'm going to identify right away is that because I'm given these binomials, I could see that they're being multiplied, which chances are you want to use the product rule. And so if we can use the product rule, great. Let's practice on using it. Okay, so what I'm going to do really quickly is I'm going to identify what is my u and what is my v. That way I can go through and I can substitute u prime times v plus v prime times u, so on and so forth. I'm going to make my substitution. That first term is going to be u, and that second term is going to be v. Okay, you know what, let's make these in a different color. There we go. So I'm going to write this on the right-hand side of the screen. I now have u being 3t minus 1, and I now have that v is t plus 2. And knowing that I'm going to have to take the derivatives of each individual piece, then identifying that u prime is going to be 3 and that v prime is going to be 1 is going to be beneficial for us. Because now when I take this derivative for dy dt, again, the change in y's with respect to t, this is now going to be my first function, which is 3t minus 1. So that's 3t minus 1. That's your first function multiplied by the derivative of the second, which is 1, plus the second function, t plus 2, multiplied by the derivative of the first function, which is just 3. And again, this first piece, this first factor, was my u. This last factor was my u prime. The second factor was my v prime, and this first factor was my v. And remember, this was the product rule that we were looking at. The product rule for derivatives, and I'm scrolling up just a little bit more, the product rule for derivatives here is at the very top of your screen that I'm using that notation, says that if we want the derivative of u times v, then we're going to have u prime times v plus u times v prime. And that's kind of what I'm looking at here. Now, you might be saying, hey, Mr. Castro, there might be a problem here. You, on your formula up there in red, had u prime times v plus v prime times u. And I'm actually going to say that because multiplication and addition are commutative with one another, then at this time, it doesn't matter whether we have v times u prime as your second term or u times v prime as our second term. It really doesn't matter because addition and multiplication are both commutative. So we're actually good here, and we can keep simplifying now. So y prime, this is going to be 3t minus 1 plus 3t plus 6, which means that y prime turns out to be 6t plus 5. All right, pretty good so far. I think so. And let's see, is there something off there? T plus 2. Okay, got that t plus 2. And then I got my derivative, and that was a 3. It's looking good. Okay, I think I got it. Awesome, great. So now that we have this, let's keep going. Let's try to do another one, and let's try to use a quotient rule this time. Let's do h of x. H of x, what if we had x plus 2 squared divided by, divided by 1 minus x. Okay, so if I have this particular case where I have this function, again, when I'm asked to take the derivative, looking at my derivative here, I'm going to identify that I need my quotient rule. So for my part C before, again, I said I was using the product rule. And in this particular case, I'm going to be using the quotient rule. So the quotient rule for us, again, says that if you can make a u and a v substitution, then do it. So I'm going to select u just to be my numerator. So u is going to be x plus 2 squared and v is going to be my denominator, where v is 1 minus x. So looking at my derivative for v prime, that's going to be negative 1. Looking at my u, well, my u is a binomial. I don't know how to take derivatives of these binomials yet to some power. So what we're going to do here is we're just going to expand. We're now left with u is equal to x squared plus 4x plus 4. And now we can take the derivative to say that the derivative u prime is going to be 2x plus 4. This last 4 is a constant, so when we take the derivative of that constant term, it just turns to 0. So now I can go through and I can start finally taking these derivatives and putting them together using my quotient rule. So the derivative with respect to x, that's a variable that we're using, for my function h of x, this is going to be the derivative of the top, in other words, derivative of the numerator, which is 2x plus 4, multiplied by my function, second function, which is 1 minus x, minus the derivative of the bottom function, which is negative 1, so which was negative 1, multiplied by my top function, which is x plus 2 squared. As such. All divided by, yowza. Let's do this. There we are. So the derivative of the the function at the bottom, that was my 1 minus x quantity squared. So I'm going to insert that 1 minus x quantity squared. There we are. Okay, so that's now looking pretty all right. So let's clean this up a little bit more. Again, I'm looking at h prime. So this is h prime of x. Is equal to, let's look at my numerator here. My numerator is actually really nice. Notice I have 2x plus 4, and what I'm going to do is I'm going to factor out a 2 from that. So I'm going to be left with 2 times x plus 2 times 1 minus x, and then negative times a negative is going to be a plus, times x plus 2 squared. All of that is still being divided by 1 minus x quantity squared. Look at that. That looks awesome. Now what I'm going to do here is I'm actually going to factor out, so again, I'm using the quotient rule down here, and what I'm going to do from the numerator, I want to factor the GCF of x plus 2. So again, on that numerator, I have a GCF of x plus 2. So I'm going to highlight that numerator because I do have that x plus 2 factor. And what I'm going to do is I'm going to use that factor to pull it out, or in that sense, factor. And we're going to be left with x plus 2 quantity. Well, for the first term, I took out that x plus 2, so I'm left with 2 times 1 minus x. Plus, the second term has 2 quantities of it, in other words, 2 copies of it multiplied by one another. If we took one of them out, then we just have x plus 2 left over. Which means the denominator is just 1 minus x quantity squared. Now we can clean up that numerator just a little bit more. And so again, this is all still h prime of x. So my numerator stays as the quantity of x plus 2. If we distribute the 2, we get 2x minus, we get 2 minus 2x. So negative 2x plus x just gets us negative x. And then finally we get 2 plus 2, which is going to be 4. So in other words, we get 4 minus x, all divided by there we go, all divided by the quantity of 1 minus x squared. And there you have it. That is your final answer. That is your derivative at the end of the day. It's nice, it's clean, and it's completely factored. Both numerator and denominator are both individually factored, which for us is a really big plus. Okay, so we have to know when to identify the product rule and when to identify the quotient rule, because again, this is going to make these differentiation operations a whole lot faster and a whole lot easier for us. So let's go through and let's work on some more differentiation problems. That way we can keep getting our feet wet with this and keep practicing. Because after all, practice makes perfect, and you want a lot of practice with these. So differentiate, here we go, differentiate the function. Part A, we have y is equal to the cube root of x multiplied by the quantity of 2 plus x. And some of you might be saying, oh yeah, we can use a product rule. Well, yeah, you'd absolutely be right, because they're asking us to take the derivative of this function, and when we take the derivative, we have to identify that we do have two terms or two factors that are multiplying one another within this one term. And so if this is the case, then we can use the product rule. So again, there are two options. We can use a product rule, or we can find a way around it. I like that last step, using or finding a way around this. What would happen if before I took a derivative, I converted cube root of x into x to the power of 1/3 multiplied by 2 multiplied by x? Okay, they're equivalent. What if instead of doing this, I distributed? X to the 1/3 times x to the power of 1, we add their exponents. So when we add their exponents, we now get 3/3, so that's going to be 4/3 to the power, or x to the power of 4/3. So when we take this derivative here, we can now bypass that product rule, and when we take this derivative, all we're going to do is drop the exponent forward, which means we're going to have 2/3 times x to the power of the numerator subtracted by 1, which is going to be negative 2/3, good so far, plus, again, drop the exponent forward, 4/3, and subtract 1 from the exponent, so minus 1, so 4/3 minus 1, that's going to be 1/3. Check that out, that is awesome. Looking pretty good so far. Now again, typically we want to factor out the negative exponents, that way we can have our derivative without any negative exponents. And if there's any common factors, we'll go ahead and we'll get those out as well. So looking at this, I have a common factor for the denominator and for the numerator. I have a 2/3, those are my common factors, x to the power of, and we take the most negative exponent that's the smallest, which will then be negative 2/3, multiplied by, well, look at the first term. I'm factoring all of that first term, which means I need a placeholder, plus 2/3 I took out of that 4/3, which means we're going to be left with 2 times x. Now, when you redistribute x to the power of negative 2/3 onto this x, remember, these exponents add. So what number added to negative 2/3 gets us 1/3? Well, that's x to the power of 1. And now our final derivative, y prime, stays as 2 multiplied by 1 plus 2x, all divided by 3 times x to the power of 2/3. And again, look at that. That derivative is beautiful because it is now completely factored. Numerator, completely factored. Denominator, completely factored. We want to make sure that our derivatives stay in such form, in completely factored form, because as we progress through the semester, we're going to keep on wanting to work with derivatives that are in this form. Now, a lot of instructors might say, oh yeah, when you take calculus, it's going to be very hard, or the algebra is going to be one of the hardest things to work with. And actually, I tell my students that the process in calculus that is going to be your best friend is factoring. Factoring is your best friend in calculus. If you know how to factor, and factoring using any technique, you will be well off. Okay, so, and this is where, as you start seeing, it starts paying off. So let's write up some tips here. So from here to here, what we did is we factored the GCF of 2/3 x to the power of negative 2/3 from these two different terms. All right, and that's pretty much it. Let's look at part B. So for part B, we're going to be working with this function. Let's go with d of t, which is going to be equal to 1 plus 16 t squared, all divided by the quantity of 4t cubed. Okay, so again, we can go through and we can say, oh yes, you know what, I see a division and we can use a quotient rule. Awesome, you'd be correct. You can use a quotient rule. But again, it's my own personal philosophy that if you can bypass either the quotient rule or the product rule, then try to do it. Now, don't start making up, random math to bypass it, but use the tools at your disposal. And that's exactly what we want to use here, is we want to use the tools at our disposal to see what we can do in order to factor this, or let's say not factor, but simplify this. So let's say that I'm working with d of t. And how do I simplify? Well, the first thing that I notice is the denominator. The denominator is a monomial. So I'm going to make sure I simplify that monomial as much as I can. 4 to the power of 3, that's going to be 64. T to the power of 3 is just t cubed. Then since it's a monomial, what I'm going to do is I'm going to take that denominator and I'm going to separate my numerator into those individual pieces. So I get that my function d of t is 1 over 64 t cubed. So 1 over 64 t cubed plus 16t squared divided by 64 t cubed. And all I need to do now is simplify just a little bit more so I can finish taking off these derivatives, or so I can start taking these derivatives. So d of t, the first term is going to be the quantity of 64, and you know what, we can actually bypass that because 64 is a constant, so we can get 1 over 64 multiplied by t to the power of negative 3 plus, we now need this 16 divided by 64. So when you take 16 and you divide it by 64, you get 1/4. So again, that 1/4 is a constant. I'm going to keep that there. T squared divided by t cubed. This is t to the power of negative 1. In other words, the t stays in the denominator. Or we get t to the power of negative 1. Great. All we need to do now is take these derivatives. So let's go ahead and take the derivatives. And notice we bypassed that quotient rule. So again, notation, d prime, derivative, drop the exponent forward. That's negative 3 over 64 times t, subtract 1 from the exponent to the power of negative 4, minus, because we're dropping this exponent, negative 1/4, times t to the power of negative 2, because we subtracted 1 from the exponent. Looking pretty good so far. Again, factor out your GCF. So what is our GCF here? Okay, so we want to factor the GCF. The GCF, well, I have a denominator of 4 that they have in common, and I also see a negative, so I'll probably want to factor out that negative as well. So let's go with negative 1/4 to start off with. Okay, that looks pretty good. And actually, I think I want to actually take something higher here. I think I want to go with 1 over 64 as my GCF. 1 over 64. That way this denominator of 4 can then have a numerator, and it'll be really nice. So negative 1 over 64, and again I'm going to take t to the power of negative 4. All right, so if we factored out that GCF, I now have, for my first term, negative 3, well, negative's already out, so 3 over 64, the 1 over 64 is gone, so I just got left 3. All right, so that's my first one, plus, because that negative got pulled out, 1 over 64. Well, now I got to think about, when I multiply 64 back in, what is 64 going to need to divide in order to get us 1/4? And that was our answer of 16. Because 16 divided by 64 gets us 1/4. And now I took out a factor of negative 4, which means that when I redistribute, this will need to be a factor of 2, or an exponent of 2. That way, when we multiply t to the power of negative 4 multiplied by t to the power of 2, we add those exponents and we get negative 4 plus 2, which is negative 2. And finally, we just clean this up. d prime of t. So I have a negative way out in the front. Numerator is 3 plus 16 t squared. Denominator is 64 t to the 4th. And again, look at that. That is awesome. Numerator completely factored. Denominator completely factored. Negative way out in the front, so that we can see that the whole fraction is negative. Now again, this is how we want all of those derivatives. So when I ask you to take a derivative either on a quiz or on an exam, then you're going to know that you need to make sure that final derivative, that answer, is completely factored. All right, let's start working with more applications, or let's not say applications, let's start working with more ideas to extract this whole concept of derivatives. So on this example, we want to find equations of the tangent line and normal lines to the curve y is equal to the square root of x, all divided by x plus 1, at the point 4, 0.4. So again, we want the equations of the tangent line and the normal line. Okay, so tangent line. So when we're looking at a tangent line, again, we're looking to take some derivative. So let me give you a really quick depiction here. Say I had a function, and this function looked like this. Say this was f of x. When we take a derivative, that derivative is going to be tangent at a specific point. And let me actually work here. There we go. So that derivative is going to be tangent to this line at a specific point. So that's going to be the tangent line. All right, and tangent line at point P. Now, if we want a normal line is going to be a line that is perpendicular to the tangent line. And remember, that normal line needs to be perpendicular to the tangent line. And so what we are focusing on here is we're going to focus on finding the equation of the tangent and finding the equation of the normal line. Well, how are we going to do that? Well, once we find the equation of the tangent line from algebra, we know how to correlate two lines that are perpendicular to one another. The way we correlate them is with their slopes. Their slopes are negative reciprocals of one another. So we're going to keep that in mind, that if we can find the slope of the tangent line, then indirectly we have found the slope of the normal line as well. And so we want to work with that. Okay, so I will expect you to know how to find tangent lines and how to find normal lines, or those equations of the normal and the tangent lines for a given curve. So that is something that you do need to know. But for now, let's keep going. So first off, let's start by finding the derivative. So I'm going to say first, find the derivative of y. In order to do this, we're going to have to use the quotient rule. Now, the quotient rule only applies in this case because we have a numerator divided by denominator with two different functions. So in order to do this, we're going to take our u, which is going to be the numerator. So I'm going to have u, which is going to be x to the power of 1/2. That's the numerator, which means my derivative, u prime, is going to be 1/2 multiplied by x to the power of negative 1/2. I'm going to have my v, which is my denominator, x plus 1, and my v prime is just going to be 1. So when I work with y prime, I'm going to take my derivative of the numerator, which is which is 1/2 x to the power of negative 1/2. So that's a derivative of the numerator, multiplied by the function at the bottom, which is x plus 1, minus the top function, which is x to the power of 1/2, times the derivative of the bottom, which is just 1. Okay, good so far. Now, the denominator, so we're going to take the bottom function, square it. So that bottom function is at x plus 1. There we are. And now we go through and we simplify the numerator. So let's keep simplifying that numerator. Again, you want to factor out a GCF. So factor the GCF of, and let's go with 1/2 x to the power of negative 1/2. So let's factor that from the numerator. Okay, so factoring from the numerator, that whole first term, I factored out the 1/2 x to the power of negative 1/2, which means we're only left with x plus 1, minus second factor. I'm factoring out 1/2, so when I distribute, I need to have a 2 remaining. That way 2 times 1/2 gets me the 1. And then x to the power of negative 1/2, I took this out, meaning I factored it. So when I redistribute, I need to have an x to multiply it by. That way the exponents add, and then negative 1/2 plus 1 should get me 1/2. And all of this is going to be divided by x plus 1 to the power of 2. Okay, that's looking great. Let's simplify a little bit more. Y prime, numerator, I now have x minus 2x, so that's just going to be minus x, so that's 1 minus x. Okay, so 1 minus x. Denominator, let's see, for that denominator, I have a 2, I have a square root of x, because that negative comes down, and I also have x plus 1 quantity squared. And there you are. That's your derivative. Now, if we want to identify the derivative at a specific point for this curve, then we can. And that's what we're going to do next. In order to find the slope of the line, that's going to be m. Okay, so I'm going to say second. Find the slope of the tangent line at x is equal to 4. And again, we're using x is equal to 4 because that's the x value that was given to us in that ordered pair. And so in order to do this, we're going to do the slope m is equal to y prime evaluated at x is equal to 4. This vertical bar just means that we're going to evaluate y prime, and then the subscript for that vertical bar is going to be x is equal to 4. Meaning we're going to make the substitutions into our y prime whenever this x value is given. So making those substitutions into our derivative will then get us 1 minus that quantity of 4, 2 times the square root of 4 times 4 plus 1 squared. All right, let's keep simplifying. 1 minus 4, that's negative 3. 2 times the square root of 4, that's another 2, so that's 2 times 2, which is 4. And then 4 plus 1, that's 5. 5 squared, that's going to be 25. 4 times 25, that's 100. So this is negative 3 over 100. Look at that. That is beautiful. That is awesome. So there's your slope. There's your slope for the tangent line at x is equal to 4. Great. And we've actually now done the really hardest part, which is find the slope. Because now we can split our problem into those two different pieces. Number one, we want to find the equation of the tangent line. Number two, we want to find the equation of the normal line to that given function at the given point. Well, we already found one of the slopes. So now let's go ahead and let's identify what's going to be the other slope that we're going to be using. Okay, so here we have the slope of the tangent line. And what I'm going to do is I'm going to denote this as the slope of the tangent line. So I'm going to do m sub t. This sub t will then signify that's the slope of the tangent line. So I'm going to say now third, find the slope of the normal line. At x is equal to 4. And now this is really more straightforward. Well, this just means we take the negative reciprocal of the slope of the tangent line. So what's the negative reciprocal? So this is going to be slope of the normal line. Then this is going to be negative times a negative, that's a positive, and then take that fraction and flip it, which is just 100 over 3. There we are. So far we found the derivative, secondly, we found the slope of the tangent line, and third, we found the slope of the normal line. Now all we have to do is put all this together into finding the equations. So let's go ahead and let's get started on that. Now, I'm going to be using the point slope form. So use the point slope form of a line to find the equations. Okay, so what's the point slope form of a line? Well, that's your y minus y1 is equal to m times x minus x1. And remember, we are given an ordered pair. The ordered pair that was given to us is the ordered pair of 4, 0.4. Okay, I'm going to actually interpret 0.4 differently. I'm going to interpret 0.4 as 4 divided by 10. And the reason I want to do this is because when I'm looking at 0.4, I'm looking at a decimal. However, look at your slopes. Your slopes are fractions. So either we want to work with fractions consistently, or we want to work with decimals consistently. And the reason I want to stay away from decimals is because 100 divided by 3, anything divided by 3 will have a repeating number unless it divides evenly. And so knowing that 100 doesn't divide evenly by 3, I know I'm going to have a recurring decimal, and I don't want an approximation. So now I'm going to work on that tangent line. So I'm going to go here, and I'm going to say that this is going to be the work for my tangent line. Okay, I'm going to extract what I know for my tangent line. Slope of the tangent line is negative 3 divided by 100. My x sub 1, again, my x coordinate is 4, and my y coordinate, the one that is given to me, is 4/10. And I'm going to make those substitutions. So y minus y1, which is 4/10, is equal to m, which is negative 3 over 100, multiplied by x minus 4. Let's go ahead and let's distribute all this in. So we have negative 3 over 100 multiplied by x, and then we're going to have negative 3 over 100 multiplied by 4. Now 4 is going to simplify your 100, but I want to kind of leave it as is, simply because I am going to have another 10 over here that I need to worry about. Or if you want, we can simplify. So let's see. I'll simplify here. 1 over 25. There we are. And then subtract this over, or add it over, plus 4/10. 4/10 actually simplifies to 2/5. Makes it a little bit nicer. Then from here we can see, hey, you know what, we can go ahead and we can add some of these values. So let's go ahead and let's start adding these values in. Alright, and I realize I caught a mistake here. The middle numerator, because we're multiplying by 3, that's 3 times 4, but 4 simplified by the 100, but the 3 still remains. There we go. And now combining our like terms, we now get that y is equal to negative 3 over 100 x, and then we have these fractions that we can add. 5 times 2 is going to be 10. 10 plus 3, that's 13 over 25. So here's the equation of your tangent line. Oh, wow, that's really nice. So this is one of the answers. Okay, let's work with the equation of the normal line. All right, so equation of the normal line. I know I'm going to be using the slope of the normal line, which we found, which was 100 over 3. Same x and y coordinates that we were given before, so x sub 1 is going to be 4, x sub 2 is going to be 4 over 10. Making these substitutions into my point slope form, I get y minus y1 is equal to m times x minus x1. Distribute everything. We get 100 divided by 3x minus 400 divided by 3 plus 4/10. And remember, you are allowed a scientific calculator. And so if you want to use a scientific calculator, you can now say, okay, well, what's going to be 4/10 minus 400 divided by 3? And you should get that this is negative 1,994 divided by 15. And again, look at this. We have no approximations here. Everything is kept exact. And again, this is the equation of the normal line. So what does this all mean, and why do we care about this when we're looking at this? Okay, so this problem was actually really, really nice in my opinion, okay, because it involves a lot of topics, a lot of concepts that we've been covering so far. So what I'm actually going to do is I'm actually going to go to GeoGebra, and we're going to look at these lines on GeoGebra and the graph, and then we'll see how all of this translates into a graphical representation. All right, so follow me along to GeoGebra. All right, so on here on GeoGebra, you'll see here we have the graph that we're initially looking at the square root of x divided by x plus 1. And the equation of the normal line, as you see here, I have the equation of the normal line in green, and that's the equation that, that's a vertical line that goes from north to south. And then we also have this other line here, which is more of an orange line that goes from left to right. And this orange line is a line that's tangent to the graph at x is equal to 4. However, if you look closely here, we do actually get to see that the normal line and the equation of the tangent line are both going to be orthogonal to one another. In other words, they're going to be perpendicular to one another. And that is what, again, we wanted to see. So now that we get to see this, and again, we're going to keep on exploring more of these topics and concepts, that we want to keep on extracting these equations of these lines, of these tangent lines, either tangent or normal. So now that we have this, let's go back to the whiteboard and let's finish off some more examples before we conclude today. All right, here we go. So on this new example, we're going to be looking to find equations of the tangent lines to the curve y is equal to x minus 1 divided by x plus 1 that are parallel to the line x minus 2y is equal to 2. So again, we want to find the equations of tangent lines, and again, they're sounds plural, so this chances are is going to be that we're going to be looking for two different tangent lines to this specific curve that are both going to be parallel to y is equal to x minus 2y is equal to 2. All right, so we want to keep that in mind. It looks like we're going to be looking for two different lines. So the reason there's going to be two different lines is because this looks like a rational function, and if I'm thinking about this correctly, which chances are it's correct, it'll look something like this. And when we're looking at the two tangent lines, it's going to be a tangent line here, and there's going to be a tangent line here. Both are going to be tangent to that given function, and both are going to be parallel to one another. So now that we've extracted that, we can now go through and we can identify what we're going to need, and more importantly, we need to identify how we're going to do this. So what I want to say here is, first, find the derivative, or the slope, of the tangent line. And you're going to notice that there are two slopes that we actually have to take into consideration here. Okay, so we're going to have to do two things, or find two of them, or let's say consider two items. Consider two restrictions. Number one, we need to find y prime. Y prime is going to give us that slope. However, the second item that we also need to consider is that the slope of the tangent line that we are working with needs to be parallel to the line that was given. So the slope of the tangent line needs to be parallel, and we're going to denote parallel as these two parallel lines, vertical parallel lines. So the slope of the tangent line will then need to be parallel to the slope of the given line. So we need these two restrictions. All right, one might be easier to find than the other, but we're going to need both of them at the end of the day. So let's find the slope of the parallel lines here. Okay, so what I'm going to do is I'm going to take my equation, x minus 2y is equal to 2, and I'm going to solve this equation for y. So if I solve this for y, this is going to be x minus 2 is equal to 2y. Divide by 2, and we get 1/2 x plus 1 is equal to y. Which means parallel lines have the same slope. So if they have the same slope, then the slope that I will be using is going to be 1/2. And in that particular instance, we found the second requirement, or the second restriction. First restriction, now we need to find y prime. So I'm going to say now find y prime. So now let's find y prime. Okay, so that's going to involve taking the derivative, and in order to take the derivative, again, we're going to need a quotient rule. So u is equal to my function in my numerator, which means that u prime will be equal to 1. V is going to be x plus 1, which means v prime is going to be 1. Making my substitutions into my derivative, y prime. Derivative of the numerator, that's going to be 1, times the function at the bottom, x plus 1, minus the derivative of the bottom, which is 1, or sorry, derivative of the bottom, which is still 1, times the function up top, which is x minus 1. And all this is going to be divided by the function at the bottom squared. So function at the bottom squared, and that bottom function was x plus 1. All right, let's simplify. Simplify as much as we can. So y prime, my numerator, I see that my x's are going to cancel, and then we're going to have a 1 on the left and negative times negative 1, so another 1, so that's going to be 2. And that's then going to be 2 divided by the quantity of x plus 1 squared. Great. So now we found y prime. But noticing that these two restrictions, well, in order for me to find the slope of my tangent line, the slope of my tangent line at a given point needs to be my y value evaluated at that point. Now, since we don't know the x value that we're going to be looking for, instead what we're going to do is we're actually going to use those two restrictions and say both of these must be equal to one another. If I know the numerical value of my slope, and if I know my function value as a slope in general for my function y, then equaling them to one another will actually solve for x and get me the x value that I need. And remember, according to this quick sketch that we did, we have two different x values. So now is when we equal them to one another. So set m sub t equal to y prime and solve for x. Great. So let's do that. 1/2 is equal to 2 divided by, x plus 1 squared. There we are. Now I'm going to cross multiply, and so when I cross multiply here, I'm going to be left with x plus 1 squared is equal to 4. Let's continue to solve. Take the square root of both sides. Taking the square root of both sides will leave me with x plus 1 is equal to plus or minus rad 4, which is plus or minus 2, which means that x is going to be two values. So x is either going to be 2 minus 1, which is going to be 1, or x is going to be negative 2 minus 1, which is negative 3. And remember, according to the picture that we saw, the quick sketch at the top right-hand corner, we can definitely see that there are two x values, one on the positive side of the y-axis and one on the negative side of that x-axis. So once we have this, we want to find those two equations, and in order to find those two equations, we then need to substitute them into the equations of the lines. So now I'm going to go over here. I'm going to split this off. There we go. So I'm going to say here, use a point slope form to find the equations. And remember, point slope form was that y minus y1 is equal to x times m times x minus x1. So we're going to have y minus y1. Well, at this time we don't know what y1 is, but we do know the x values. Okay, so let's go ahead and let's extract first that if we have an x value of 1, plug this 1 into the equation. Well, if x is 1, and I'm going to do this right below, if x is 1, your y output using the function that we were given, so this function that we were given, the y is equal to x minus 1 divided by x plus 1, plug in 1. Well, if we plug in 1, then we naturally get 0. Okay, not looking too bad. What about if we plug in 3, or negative 3? Well, if we make the substitution of negative 3, then again our function value is going to be negative 3 minus 1, which is negative 4. Then negative 4 divided by negative 3 plus 1, which is negative 2. So that should be a y value of 2. So my ordered pairs here are 1, 0, and they're also going to be negative 3, 2. So back to what I was saying here, that I need the equations of the lines. Y minus y1, in this case it's y minus 0, is equal to m, and I'm going to use one of my slopes here. Well, my slope is positive, so that's going to be 1/2 x minus x1, which is 1, which means y is equal to 1/2 x minus 1/2. We found one equation. Let's find the other. Y minus 2 is equal to m, same slope, times x minus x1, so x minus x1, which is going to be plus 3. Distribute and simplify, that's 1/2 x plus 3/2. 3/2 minus 2, that should be 7/2. Or sorry, plus 2 should be 7/2. And those are the two equations that are tangent to that given graph. And as we saw up here, yes, they now have the same slope. Having the same slope but different y-intercepts would then classify them as parallel lines. Wow. So that is pretty amazing. So again, I hope that you all enjoyed this lesson. And again, we're going to keep doing more work on taking derivatives and finding equations of tangent lines based on those derivatives that we find. So again, I hope you all enjoyed this lesson, and I hope to see you all back for the next one. Till then, have a good day.